Well, let me ask you a question that's probably kept you awake at night at some point. It's one of those questions that seems simple on the surface, but when you start to unpack it, when you really sit with it and explore it, it becomes something profound, almost unsettling. The question is this: what existed before the Big Bang? Now, I know what you're thinking. Brian, haven't you told us that the Big Bang was the beginning of everything, the beginning of space, time, matter, energy? How can there be a before if time itself started there? And you're right to think that. It's exactly the kind of response physicists have been giving for decades. Time began at the Big Bang. So asking what came before is like asking what's north of the North Pole. The question doesn't make sense because you've reached the boundary of the concept itself. But here's the thing, and this is what makes this topic so fascinating. We're not entirely sure that's the right answer anymore. Physics has this wonderful way of taking questions that seem to have settled answers and then revealing layers of complexity we hadn't anticipated. And the question of what came before the Big Bang, or whether before even makes sense in this context, is one of those questions that's been cracked wide open by recent theoretical developments. So let me take you on a journey. We are going to start with what we know, the solid, well-established science of the Big Bang. Then we are going to venture into more speculative territory, exploring ideas that physicists are seriously considering about what might have preceded our universe or what larger reality our Big Bang might be embedded in. And I want to be clear from the start, we don't have all the answers here. We might not have any definitive answers for decades or even centuries. But what we do have is a set of fascinating possibilities. Each one grounded in serious physics. Each one telling us something profound about the nature of reality. Let's begin with what we actually know. The Big Bang theory is one of the great triumphs of 20th century science. It tells us that about 13.8 billion years ago, the universe was in an extraordinarily hot, dense state. And from that state, it's been expanding and cooling ever since. Now, when I say expanding, I don't mean that matter is flying outward into empty space. I mean that space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. How do we know this? Well, we have multiple lines of evidence that all point to the same conclusion. First, we observe that distant galaxies are moving away from us, and the farther away they are, the faster they are receding. This was discovered by Edwin Hubble in the 1920 seconds. And it's exactly what you'd expect if space itself is expanding. If you run the expansion backward in time, everything converges to a point, or more accurately to an extremely hot, dense state about 13.88 billion years ago. Second, we have the cosmic microwave background radiation. This is light that was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. This ancient light has been traveling through space ever since. And we can detect it today as a faint microwave glow coming from every direction in the sky. It's the oldest light in the universe, and it carries a wealth of information about the early cosmos. Third, we can calculate what elements should have been formed in the first few minutes after the Big Bang, when the universe was hot enough for nuclear fusion. And when we look at the universe today, the abundances of light elements like hydrogen, helium, and lithium match those predictions remarkably well. It's like finding a fingerprint that confirms the story. So, the Big Bang theory is solid. It's well tested, well confirmed, as good as any theory in science. But, and this is crucial, the Big Bang theory describes how the universe evolved from a hot, dense state. It doesn't necessarily explain what caused that state or what, if anything, came before it. Now, let me walk you through what happened in those early moments, because understanding the timeline is important for grasping why the before question is so tricky. And I mean, this timeline is extraordinary. We are talking about events that happen in fractions of a second at temperatures and densities that are almost beyond comprehension. Let's start at the very beginning. The Planck epoch. This is the first 10⁻⁻43 seconds after the Big Bang. That's a decimal point followed by 42 zeros and then a 1. It's an almost incomprehensibly short time. To give you a sense of scale, there are more Planck times in 1 second than there have been seconds since the Big Bang. During this period, the universe was so hot, so dense, so extreme that our current laws of physics, general relativity, and quantum mechanics probably don't apply. We'd need a theory of quantum gravity to understand this epoch. And we don't have a complete theory of quantum gravity yet. So, right away, we hit a limit. We can't confidently say what happened in the very first moments. We can speculate. We can explore possibilities, but we are working at the edge of our theoretical understanding. And that's both humbling and exciting. It's humbling because it reminds us how much we still don't know. But it's exciting because it means there are still profound mysteries to solve. After the Planck epoch, we enter a period that might have involved cosmic inflation. This is where things get really interesting. The idea developed in the 1980 seconds by Alan Guth and then refined by Andre Linde, Paul Steinhardt and others is that the universe underwent a period of extraordinarily rapid expansion. I mean extraordinarily rapid. We are talking about the universe growing by a factor of at least 10 to the 26. That's 100 trillion in a tiny fraction of a time second, maybe 10 theos 35 seconds. Now why would the universe do this? Well, here's where we need to talk about a concept that might seem strange at first. Repulsive gravity. You see, we are all familiar with gravity as an attractive force. The Earth pulls you down. The Sun holds the planets in orbit. That's ordinary gravity created by massive objects. It's the gravity we experience every day of our lives. But Einstein's equations actually allow for another kind of gravity, repulsive gravity. Instead of pulling things together, it pushes things apart. And this isn't just a mathematical curiosity. We think repulsive gravity is real. And in fact, we see evidence for it in the universe today in the form of dark energy, which is causing the expansion of the universe to accelerate. The key is this. Ordinary attractive gravity is produced by matter and energy that's clumped together like a planet or a star. But repulsive gravity is produced by energy that's spread uniformly through space. If you have a field, we call it the inflating field, though the name doesn't really matter. If you have a field that fills space uniformly with energy, then according to Einstein's equations, it produces repulsive gravity. So here's the picture. In the earliest moments, the universe might have been filled with this inflating field. The energy in this field produced repulsive gravity, and that repulsive gravity drove inflation. Space expanded at an incredible rate, doubling in size over and over again in rapid succession. It's like taking something the size of an atom and inflating it to the size of a galaxy or even much larger in a fraction of a second. It's mind-boggling. And then inflation ended. The inflating field decayed and its energy converted into ordinary matter and radiation. This is what we call the hot Big Bang. And the moment when the universe became filled with particles and light at enormous temperatures. From that point on, the universe expanded more gradually, cooling as it grew. Now, let me give you a sense of the timeline from that point forward because the precision with which we understand this is really remarkable. At 1 second after the Big Bang, the universe was a sea of particles, neutrons, protons, electrons, positrons, photons, neutrinos at a temperature of about 10 billion Kelvin. That's hot enough that atomic nuclei can't hold together. In fact, it's so hot that protons and neutrons themselves are barely stable. At about 2 minutes, the temperature had dropped to around 1 billion degrees, cool enough for nuclear fusion to occur. Protons and neutrons combine to form the nuclei of light elements, mostly hydrogen and helium with a little bit of lithium and trace amounts of beryllium and boron. This process called Big Bang nucleosynthesis lasted for only a few minutes. After that, the universe had cooled too much for fusion to continue. But in those few minutes, about 25% of the protons in the universe combined with neutrons to form helium nuclei. That ratio, roughly 3 parts hydrogen to 1 part helium by mass, is what we observe in the universe today. And it's one of the great confirmations of the Big Bang theory. For the next few 100,000 years, the universe was filled with a plasma of nuclei and electrons. Too hot for atoms to form. This plasma was opaque light. Couldn't travel far because it kept scattering off the free electrons. The universe was like a fog, or maybe better, like being inside a star. You couldn't see through it. Then at about 380,000 years, something remarkable happened. The temperature dropped to around 3000 degrees Kelvin. That's still pretty hot, hotter than any oven you've ever used, but it's cool enough for electrons to combine with nuclei and form neutral atoms. This moment is called recombination, though that's actually a misnomer because it wasn't a recombination. It was the first time atoms had ever formed, but the name has stuck. Recombination is a crucial moment in cosmic history because once atoms formed, light could travel freely. The universe became transparent. And the light that was released at that moment, the last light to scatter off electrons before atoms formed, is what we see today as the cosmic microwave background radiation. It's been traveling through space for 13.88 billion years, stretched by the expansion of the universe from visible light to microwaves. When we look at the cosmic microwave background, we're seeing the universe as it was at 380,000 years old. It's our earliest baby picture of the cosmos and it's extraordinarily detailed. After recombination, the universe entered what's sometimes called the cosmic dark ages. There were no stars yet, no galaxies, just atoms of hydrogen and helium drifting through space in the dark. But those atoms weren't distributed perfectly uniformly. There were tiny variations in density, regions that were slightly denser than average and regions that were slightly less dense. These tiny ripples, just 1 part in 100,000, were left over from quantum fluctuations during inflation. And those ripples, amplified by gravity over hundreds of millions of years, eventually grew into the galaxies and galaxy clusters we see today. The first stars probably formed a few 100 million years after the Big Bang. We're not entirely sure of the exact timing, but observations from the James Webb Space Telescope are pushing that date earlier and earlier. These first stars were different from the Sun. They were massive, maybe 100 or even 1,000 times the mass of the Sun, made purely of hydrogen and helium because no heavier elements existed yet. And they lived fast and died young, exploding as supernova after just a few million years and enriching space with heavier elements. Those heavier elements, carbon, oxygen, nitrogen, iron, and so on, became the building blocks for later generations of stars, for planets, and ultimately for life. Every atom in your body except for hydrogen was forged in the nuclear furnaces of stars or in supernova explosions. We are quite literally made of stardust. Carl Schurz said it beautifully. We are a way for the cosmos to know itself. Now that's the standard story and it's well supported by observations. But notice what I haven't explained. Why did the Big Bang happen in the first place? What set up the initial conditions? What created the inflating field? And crucially, what if anything existed before? For a long time, the standard answer was that the question doesn't make sense. If time itself began at the Big Bang, then there is no before. It's like asking what's south of the South Pole. You can't go any further south because you've reached the limit of the concept. The South Pole isn't a wall or a boundary. It's just the point where all lines of longitude converge. In the same way, the Big Bang might be the point where time itself begins. And asking what came before is asking a question that doesn't have meaning within the framework of our physics. And you know, there's a certain elegance to that answer. It's clean. It's definitive. It respects the mathematics of general relativity, which tells us that spacetime itself breaks down at the Big Bang singularity. But it also feels unsatisfying, doesn't it? It feels like we're avoiding the question rather than answering it. We're saying the question doesn't make sense when what we really mean is our current theories can't answer it. So physicists started exploring other possibilities. And what they found is that there are multiple ways the universe could have come into being, multiple scenarios that extend beyond the Big Bang and suggest that our cosmic origin might be more complex than we thought. And these aren't just wild speculations. These are serious proposals grounded in extensions of well-tested theories worked out in mathematical detail by some of the best physicists in the world. Let me tell you about one of the most intriguing ideas, eternal inflation. Now remember I mentioned that inflation was driven by this inflating field that filled space uniformly. Well, here's the thing. Quantum mechanics tells us that fields don't sit perfectly still. They fluctuate. At any given point in space, the value of a field can go up or down randomly due to quantum uncertainty. It's like the field is jittering, vibrating at a quantum level. In most contexts, these fluctuations don't matter much. They are tiny and they average out. But in the early universe when inflation was occurring, they mattered a lot. In some regions of space the inflating field would fluctuate downward. The energy would decrease. Inflation would end. And that region would have its own hot Big Bang. It would become a universe of matter and radiation expanding and cooling and eventually forming galaxies and stars. But in other regions, the inflating field would fluctuate upward. The energy would increase and inflation would continue. And here's the remarkable thing. Inflation makes space expand so rapidly that even though inflation is ending in some regions, creating these bubble universes, the regions where it continues are growing even faster. So the total volume of space where inflation is happening keeps increasing. This is eternal inflation. Once inflation starts somewhere anywhere, it never completely stops. It ends here and they are creating bubble universes like ours. But it keeps going in between those bubbles, spawning more and more bubble universes forever. And each bubble universe has its own Big Bang, its own expansion, its own history, its own galaxies and stars, and potentially its own planets and life. So in this picture, our Big Bang wasn't the beginning of everything. It was the beginning of our bubble, our local region of space. But there's a larger space, perhaps infinitely large, that's been inflating for much longer, maybe forever. And that larger space is constantly spawning new bubble universes, each with its own Big Bang. Think about it like boiling water. You know how when you heat water, bubbles start forming at the bottom of the pot. Each bubble nucleates at a point, then expands rapidly as it rises. Our universe is like one of those bubbles. We can see the inside of our bubble. That's our observable universe stretching out 13.88 billion light-years in every direction. But we can't see outside our bubble because the space between bubbles is expanding faster than light can travel across it. We're trapped inside our cosmic bubble forever, cut off from the other bubbles in the eternal inflating sea. Now, if this is true, it answers the question, what existed before the Big Bang in a very concrete way. What existed before was this larger inflating space, and what caused our Big Bang was the end of inflation in our particular region. The inflating field decayed here. Its energy converted to matter and radiation, and our universe began its expansion and cooling. But in a sense before is the wrong word because time in the larger inflating space isn't the same as time in our bubble. Each bubble has its own time and they are not synchronized. But of course, you might be thinking, okay, but this just pushes the question back, right? Where did the inflating space come from? Where did the inflating field come from? We haven't really explained the ultimate origin. We've just expanded the scope of what needs explaining. And you're absolutely right. We have pushed the question back, but that's actually progress. We've learned that the Big Bang and the beginning of everything might not be the same thing. We've learned that the universe might have much more structure, much more history than we can directly observe. We've learned that our cosmic horizon, the limit of what we can see, might not be the limit of what exists. And here's something even more wild. In this eternal inflation scenario, there's no reason to think that all of these bubble universes have the same properties. You see, in physics, we often talk about something called symmetry breaking. This is the idea that as a system cools or changes state, certain symmetries can break in different ways, like water freezing into ice crystals with different patterns. Well, in different bubble universes, the symmetries of the laws of physics might break in different ways. What does that mean practically? It means that the fundamental constants of nature, things like the strength of gravity, the mass of the electron, the strength of the electromagnetic force, the cosmological constant, those might be different in other bubble universes, not just by a little bit, but potentially by a lot. And the laws themselves, the number of forces, the types of particles that exist, even the dimensionality of space, those could be different, too. String theory, if it's correct, suggests there might be something like 10 to the 500 different possible ways that the extra dimensions could be configured. Each one corresponding to a different set of physical laws. That's called the string theory landscape. That's an enormous number. I mean, to put it in perspective, the number of atoms in the observable universe is maybe 10 to the 80. So, we're talking about vastly more possible universes than there are atoms in our universe. It's almost incomprehensible. And if eternal inflation is real, then all of those possibilities might be realized somewhere in the eternally inflating multiverse. Now, This leads to a really interesting question, one that's somewhat controversial among physicists. If there are all these bubble universes out there with different properties, why does our universe have the properties it does? Why is gravity exactly the strength it is? Why is the electron exactly the mass? Why is the cosmological constant, the energy density of empty space, so extraordinarily small compared to what we'd naively expect? For a long time, physicists hoped we'd find some deep principle, some fundamental symmetry or mathematical requirement that would explain why the constants have the values they do. We hoped we'd be able to say the constants must be these values because anything else would violate this principle or that symmetry. But what if there's no such principle? What if the constants are just environmental variables that vary from one bubble universe to another? Like the temperature or the humidity varies from place to place on Earth. In that case, asking why our universe has the properties it does might be like asking why Earth is the right distance from the Sun for liquid water. There's no deep principle. It's just that if Earth were much closer or much farther, we wouldn't be here to ask the question. We find ourselves on a planet with liquid water because life requires liquid water. It's selection bias, pure and simple. In the multiverse context, this is called the anthropic principle. The idea is that we shouldn't be surprised to find ourselves in a universe with properties that allow for our existence because those are the only universes where there are beings like us to observe anything. It's not that our universe is special in an absolute sense. It's just special to us because we exist in it. Now, I know this makes some people deeply uncomfortable. It feels like we're giving up on finding a deeper explanation. It feels like we're saying the universe is the way it is because if it weren't, we wouldn't be here to wonder about it. And that sounds like a cop-out, like we're not really explaining anything. But here's the thing. If the multiverse is real, then that is the deeper explanation. The explanation is that all the possibilities are realized somewhere in the eternally inflating landscape and we necessarily find ourselves in one that allows for our existence. That's not giving up on explanation. It's accepting what the theory tells us about the structure of reality. Of course, and this is crucial, we don't know if eternal inflation is correct. We don't know if the multiverse is real. It's a consequence of taking inflation and quantum mechanics seriously and following the mathematics where it leads. But inflation itself, while supported, isn't proven beyond all doubt. And even if inflation happened, eternal inflation might not be inevitable. There might be mechanisms that shut it off globally. And in fact, one of the biggest challenges with the multiverse idea is figuring out how to test it. Because here's the problem. If these other bubble universes are beyond our cosmic horizon, if they're regions of space from which light can never reach us because the space between us is expanding faster than light can cross it, then how can we ever observe them? How can we ever confirm that they exist? This is a real challenge and different physicists have different views on it. Some say that if a theory makes predictions about our universe that we can test and those predictions turn out to be correct, then we should take seriously the other things the theory tells us even if we can't directly observe them. In this view, the multiverse would be like the far side of the moon. Before we sent spacecraft around it, we couldn't see it directly, but we had good reason to think it was there. Based on our understanding of gravity and orbital mechanics. Others say that's not good enough. They say that if we can't observe something even in principle, then it's not science, it's philosophy or metaphysics. And they have a point too. Science has always been about making predictions that can be tested against observations. If a theory makes no testable predictions, how is it different from any other story we might tell? My own view is somewhere in between. I think we should take these ideas seriously. We should work out their implications. We should look for any possible observational signatures. But we should also remain humble and open to the possibility that we might be on the wrong track entirely. That the real answer might be something we haven't thought of yet. Now, there might be indirect ways to test the multiverse idea. For example, if two bubble universes collided in the past, it might leave a signature in the cosmic microwave background, a circular pattern of temperature variations that we could detect. Several groups have looked for such signatures. And so far, they haven't found any. But that doesn't mean they are not there. They might be too subtle to detect with current instruments, or they might be in a part of the sky we haven't examined carefully enough. Another possibility is that the string theory landscape might have patterns or structures that we can predict. Maybe certain combinations of constants are more common than others. Or maybe there are correlations between different constants. If we could figure out those patterns, we might be able to make statistical predictions about what we should observe in our universe. But I'll be honest with you, these are long shots. Testing the multiverse is incredibly difficult and it might turn out to be impossible. We might never know for sure whether other bubble universes exist. And that's frustrating because as a physicist, I want to know the answer. I want to understand the full structure of reality, not just the part one can see from inside my cosmic bubble. But even if we can't directly confirm the multiverse, the journey of exploring the idea has value. It's taught us to think more carefully about what it means for a scientific theory to be testable. It's pushed us to develop new mathematical techniques and new conceptual frameworks. And it's opened our minds to the possibility that reality might be much larger and stranger than we ever imagined. Let me give you another way to think about the before the Big Bang question. One that's quite different from eternal inflation. This approach takes seriously the idea that time itself might have a beginning, but it tries to make sense of that beginning using quantum mechanics. You're probably familiar with some of the weirdness of quantum mechanics. Particles can be in multiple states at once, what we call superposition. An electron can be here and there simultaneously until you measure it and then it chooses one location or the other. The act of measurement somehow collapses the superposition into a definite state. It's bizarre. It's counterintuitive, but it's been confirmed by countless experiments. Now, what if we apply this quantum weirdness not just to particles, but to the universe as a whole? What if the universe itself can be in a superposition of states? What if spacetime itself is subject to quantum uncertainty? This is the realm of quantum cosmology and it leads to some really mind-bending ideas. One of the most famous is the Hart-Hawking no-boundary proposal developed by James Hartland Stephen Hawking in the 1980s. The basic idea goes like this. In quantum mechanics, we describe the state of a system using something called a wave function. For a single particle, the wave function tells you the probability of finding the particle at different locations. For a collection of particles, the wave function describes all the possible configurations of those particles and their probabilities. Hadel and Hawking proposed that we should think of the universe itself as having a wave function, a quantum state that describes all possible configurations of spacing. Now in general relativity, space and time are woven together into a single fabric called spacetime. And the shape of spacing can curve and warp depending on how matter and energy are distributed. What Hartle and Hawking did was use a mathematical trick, a technique called Euclidean time, where time is treated as if it were another dimension of space to calculate the wave function of the universe. And what they found was remarkable. There's a solution where the universe has no boundary in time, no beginning, no moment of creation. The geometry of spacetime is smooth and closed like the surface of a sphere. Think about the surface of the Earth. If you start at the equator and walk south, you eventually reach the South Pole. And at the South Pole, you can't go any further south. But there's no wall there, no edge, no boundary. The South Pole is just a point where all the lines of longitude meet. It's a perfectly smooth part of the surface just like any other point. In the same way, in the Hart-Hawking proposal, the Big Bang is like the South Pole of spacetime. You can't go further back in time. Not because there's a boundary or a wall, but because the geometry of spacetime is such that the question, what came before, doesn't have meaning. Time itself emerges smoothly from this quantum geometry. There's no moment of creation. No first instant. Time just is as part of the structure of the universe. Hawking liked to say, what lies north of the North Pole? And the answer is nothing. Not because there's literally nothing there, but because the question doesn't make sense given the geometry of the Earth. Similarly, what came before the Big Bang might not make sense given the quantum geometry of spacing. Now, I want to be really clear about what this does and doesn't say. It doesn't say that the universe popped into existence out of nothing. It says that time itself is a feature of the universe, not something the universe exists in. The universe in this view just is. It's a self-contained four-dimensional geometry with no boundary and no need for an external cause or a moment of creation. Is this right? We don't know. The mathematics is elegant and beautiful, but it's incredibly hard to test. One of the challenges with quantum cosmology, that's the field that tries to apply quantum mechanics to the universe as a whole, is that we typically test quantum mechanics by doing the same experiment many times and looking at the statistics of the outcomes. We prepare a particle in a certain state, measure it, record the result, we do it again and again, thousands or millions of times, and we build up statistics. But we only have one universe to observe. We can't run the experiment multiple times. We can't prepare the universe in a certain quantum state and then measure it to see what happens. We get one shot, one observation, and that's it. So testing quantum cosmology is inherently difficult. However, there are potential observational signatures. The no-boundary proposal makes predictions about the structure of fluctuations in the early universe. Those tiny ripples I mentioned that eventually grew into galaxies. These fluctuations would have a certain statistical pattern, a certain spectrum if you will. And we can observe that spectrum in the cosmic microwave background. So far the observations are consistent with the no-boundary proposal, but they are also consistent with other ideas. We need more precise measurements to really distinguish between different quantum cosmology models. And we are getting those measurements. Every new generation of telescopes and detectors gives us more detailed information about the cosmic microwave background. And we are slowly but surely constraining the possibilities. Now, there's yet another idea I want to tell you about. One that comes from string theory and involves extra dimensions. I've mentioned string theory a few times. So, let me briefly explain what it is. String theory is a candidate for a theory of quantum gravity. A theory that would unify general relativity and quantum mechanics. The basic idea is that the fundamental building blocks of nature aren't point-like particles, but tiny vibrating strings of energy. Different vibration patterns correspond to different particles. One pattern gives you an electron, another gives you a quark, another gives you a photon, and so on. One of the peculiar features of string theory is that it requires extra dimensions of space beyond the three we experience. Depending on the version of string theory, there might be 6 or 7 extra dimensions. Now, you might wonder why we don't see these extra dimensions. The standard answer is that they are compactified. They are curled up so small that we don't notice them. Imagine an ant walking on a garden hose. To the ant, the hose looks one-dimensional. You can walk forward or backward along it. But if you zoom in, you'll see that there's actually another dimension curled up into a tiny circle. The extra dimensions in string theory are like that curled up at the Planck scale about 10 or 35 m, far too small for us to directly observe. But there's another possibility, one that was developed by physicists like Lisa Randall and Roman Sundrom in the late 1990s. What if some of the extra dimensions aren't compactified? What if they are large but were confined to a three-dimensional surface, a brain embedded in this higher dimensional space? Imagine you're an ant walking on a tightrope stretched across a room. To you, the tightrope is your entire universe. You can walk forward and backward along it, but you can't leave it. You're confined to this one-dimensional path, but the tightrope itself exists in three-dimensional space. There's a whole room out there. You just can't access it because you're stuck on the tightrope. In the brain world scenario, we're like that ant. We're confined to a three-dimensional brain, but this brain exists in a higher dimensional space, which physicists call the bulk. And there might be other brains out there, floating in this higher dimensional bulk, completely separate from ours. Now, here's where it connects to the Big Bang. What if our Big Bang was caused by a collision between two brains? Imagine two of these three-dimensional surfaces floating in the higher dimensional space drifting toward each other due to some force or field. They collide and the enormous energy of that collision converts into the hot dense state we call the Big Bang. The expansion and cooling of the universe afterward is just the aftermath of this collision, like the ripples spreading out on a pond after you drop a stone into it. This is called the epiroic model from the ancient Greek word esaurosis, which refers to a cosmic conflagration, a periodic destruction and recreation of the world. The apoiotic model was developed by Paul Steinhardt, Neil Turok, and others in the early 2000s, and there's a variant of it called the cyclic model where these brain collisions happen over and over again cyclically. Here's how it would work. Two brains collide, creating our Big Bang. The universe expands and cools. Galaxies form. Stars are born and die. Planets form. Life emerges. But the brains are still attracted to each other by some force. Eventually, over trillions of years, the expansion slows, stops, and reverses. The brains come back together. This would be a big crunch. And then they collide again, creating a new Big Bang. And the cycle repeats. Big Bang expansion, big crunch, Big Bang, expansion, big crunch, over and over, extending infinitely into the past and infinitely into the future. In this picture, time doesn't have a beginning. Time is eternal. And the Big Bang is just one event in an endless series of events. So when you ask what existed before the Big Bang, the answer is the previous cycle. There was another universe before ours. It collapsed in a big crunch and the energy of that collapse seeded our Big Bang. Now what I find fascinating about the cyclic model is that it addresses a question that's bothered a lot of physicists. If the universe began at the Big Bang, what set up the incredibly special initial conditions we seem to need? Why was the universe so smooth and uniform? Why was the distribution of matter and energy so finely tuned? In the standard Big Bang picture, you have to just assume these special initial conditions. But where did they come from? The cyclic model says the initial conditions weren't special at all. They were determined by what happened in the previous cycle. Each cycle, the universe expands, structure forms, things get messy and complicated. But then during the contraction phase and the bounce, there's a kind of cosmic reset. The details get smoothed out. Entropy gets redistributed. And you get a fresh start with the next Big Bang. It's like shuffling a deck of cards over and over. Eventually, the memory of the initial order is lost and you approach a kind of statistical equilibrium. But there are problems with the cyclic model too. One issue is entropy. The second law of thermodynamics says that entropy, roughly speaking, the amount of disorder should always increase. But if the universe goes through infinite cycles, why isn't it at maximum entropy already? Why is there still structure, still stars and galaxies, still gradients and energy flows that can drive interesting processes like life? The cyclic model has ways of addressing this. Maybe entropy resets at each bounce, or maybe the universe gets bigger with each cycle, so there's always room for entropy to increase. But these are subtleties that require careful analysis and not everyone is convinced by the answers. Another issue is what happens at the bounce itself. When the brains collide, you get an enormous release of energy and you need that energy to be distributed smoothly enough to give you the uniform Big Bang we observe. Does the collision really do that? The calculations are tricky and there's debate about whether the bounce is smooth or whether it creates problematic irregularities. So the cyclic model, like eternal inflation and the no-boundary proposal, is an idea we're exploring, not an established fact. It might be right, it might be wrong, or the truth might be something that incorporates elements of several different ideas. Now, I want to take a step back and talk about what all of these scenarios have in common. Whether it's eternal inflation with its eternally spawning bubble universes, or the no-boundary proposal where time emerges smoothly from a quantum state, or the cyclic model with its endless sequence of big bangs and big crunches. They all represent attempts to extend our understanding beyond the Big Bang. They are all ways of trying to answer the question, what existed before or what caused it? Even when naive intuition says those questions might not make sense. And what's remarkable is that we're not just making up stories. We're using mathematics, the same mathematics that has proven spectacularly successful in describing the universe we can observe. We are taking theories like general relativity and quantum mechanics and string theory, theories that have been tested and confirmed in many contexts, and we are extrapolating them to these extreme regimes. Now, extrapolation is always risky. When you take a theory beyond the domain where it's been tested, you might be getting nonsense. But it's also how we make progress. Einstein's general relativity was confirmed with very high precision in weak gravitational fields. The motion of planets around the sun, the bending of starlight by the sun's gravity. But we use it to describe black holes and neutron stars and the Big Bang regimes of gravity far more extreme than anything Einstein could test in his lifetime. And you know what? It works. The theory even in these extreme regimes has proven remarkably reliable. So when we use the same mathematical framework to think about what might have existed before the Big Bang, we're not just guessing randomly. We are making educated extrapolations based on theories that have earned our trust. That doesn't mean we're right, but it means we have reasons for taking these ideas seriously. And in the next part of our journey, we're going to explore what these different scenarios really mean for how we understand time, causation, and the nature of existence itself. Because this isn't just about cosmology. It's about the deepest questions we can ask. What is time? Can it have a beginning? What does it mean for something to cause something else? Why is there something rather than nothing? These are questions that have fascinated philosophers for millennia. And for the first time in history, we have the tools, mathematical, observational, conceptual, to make real progress on them. We are not just philosophizing. We are doing physics. We are developing theories, working out their predictions, looking for ways to test them. And occasionally we are finding clues in the cosmic microwave background or in the distribution of galaxies or in the properties of the universe that tell us something profound about its origin. So in part 2, we're going to dive deeper. We are going to explore what eternal inflation really implies about the nature of reality. We are going to look more carefully at the no-boundary proposal and what it means for time to emerge rather than exist absolutely. We are going to think about cyclic models and whether time can be eternal. And we are going to consider the widest idea of all. That the universe might have literally come from nothing through a quantum tunneling process that defies our everyday intuitions about how reality works. Because here's the thing, when you're dealing with the origin of the universe, when you're asking about what came before the Big Bang, you're working at the very edge of physics. You're in a regime where space and time themselves might break down, where quantum mechanics and gravity intertwine in ways we don't fully understand, where the very concepts we use to think about reality might not apply. And in that regime, we should expect the unexpected. We should expect ideas that violate our intuitions, that challenge our assumptions, that force us to rethink everything we thought we knew. And that's exciting. That's what makes physics at the frontier so compelling. We are not just filling in details. We are potentially revolutionizing our understanding of the most basic features of reality. Space, time, matter, energy, causation, existence itself. So stay with me. Part 2 is where things get even more interesting, where we really push into the strange and wonderful possibilities that modern physics has opened up. We are going to explore ideas that might seem crazy at first, but that are grounded in serious mathematics and taken seriously by physicists working at the cutting edge of cosmology and quantum gravity. The question, what existed before the Big Bang, doesn't have a simple answer. It might not have a single answer. But exploring the possibilities, following the mathematics, thinking deeply about what our theories tell us. That's how we push the boundaries of human knowledge. That's how we take the next step in our cosmic journey of understanding. So, we've established that the question, what existed before the Big Bang, opens up into remarkably deep territory. We've talked about eternal inflation and its multiverse of bubble universes, about the Hadar-Hawking no-boundary proposal where time emerges from a quantum state, and about cyclic models where Big Bangs repeat eternally. Now I want to take you deeper into what these ideas really mean. And I want to introduce some additional scenarios that push our understanding even further. Let me start by being really clear about something that often gets muddled in discussions about the Big Bang. When cosmologists talk about the Big Bang, we're talking about the evolution of the observable universe from a hot dense state 13.8 billion years ago. We're not necessarily talking about the creation of all of space or the beginning of time itself. That's a crucial distinction, and it's one that opens up a lot of conceptual room. The observable universe, that's the region of space from which light has had time to reach us over the past 13.8 billion years. It's a sphere centered on us with a radius of about 46 billion light-years. Now, you might think, wait, if the universe is only 13.88 billion years old, shouldn't the observable universe only be 13.8 billion light-years across? But remember, space itself has been expanding. Light that was emitted 13.8 billion years ago has been traveling toward us all that time, but the space it was traveling through was stretching. So that light is now coming from regions that are much further away than 13.88 billion light-years. But here's the key point. The observable universe is not necessarily the entire universe. The whole universe could be much, much bigger. It could even be infinite in extent. And if it's infinite now and it's been expanding then, and this is counterintuitive, it was also infinite in the past. An infinite universe that's expanding doesn't shrink to a finite size as you go backward in time. It just gets denser. The spacing between things decreases, but the total extent remains infinite. So right away we can imagine scenarios where the Big Bang wasn't the beginning of all space. It was the beginning of the expansion and cooling that created our observable universe. But there might be vast regions of space beyond our horizon that have their own histories, their own dynamics. Now let me take you back to eternal inflation because I want to explore its implications more deeply. Remember, in eternal inflation, once inflation starts somewhere, it never completely stops. It ends in some regions creating bubble universes, but it continues in other regions, and those regions are growing faster than the bubbles are forming. So you have this eternally inflating background space that's constantly spawning new universes. Think of it like a pot of boiling water. But imagine that the water never stops boiling and new bubbles are forming forever. Each bubble is a universe. Our universe is one bubble. We are inside it. We can see its interior, but we can't see outside because the space between our bubble and neighboring bubbles is expanding too fast. Light from those other universes can never reach us. Now, here's where it gets really interesting. In different bubble universes, the laws of physics might be different. Not just the values of the constants, not just the strength of gravity or the mass of the electron, but the actual laws themselves. The number of forces, the types of particles, even the dimensionality of space might vary. How can this be? Well, in modern physics, particularly in string theory, we think of the laws of physics as being determined by something called the vacuum state. The vacuum isn't empty. It's the lowest energy state of all the quantum fields that permeate space. And there might be many different possible vacuum states, each one corresponding to a different set of physical laws. It's a bit like ice. Water can freeze into different crystal structures depending on the temperature and pressure. Each crystal structure has different properties, different symmetries, different densities. In the same way, the quantum field of the universe can freeze into different vacuum states as the universe cools. And each vacuum state gives you a different physics. String theory suggests there might be an enormous number of possible vacuum states, maybe 10 to the 500 or more. Each one is a different way the extra dimensions can be configured, and each configuration gives you different particles, different forces, different constants. This vast collection of possibilities is called the string theory landscape. Now in eternal inflation, all of these possibilities might be realized. In some bubble universes, the vacuum settles into one configuration. In others, it settles into a different configuration. It's like rolling dice. Each universe gets a different roll, a different set of physical laws. And this brings us to a profound question. Why does our universe have the laws it has? Why does gravity have the strength it does? Why are there 3 generations of matter particles? Why is the cosmological constant, the energy density of empty space, so extraordinarily small? For decades, physicists hoped we'd find some deep principle that would explain these things. We hoped we'd discover some symmetry or mathematical requirement that would force the constants to have exactly the values they do and no other values. We wanted to be able to say the universe must be this way because anything else would violate this fundamental principle. But what if there's no such principle? What if the constants are just environmental accidents varying from one bubble universe to another? Like the temperature varies from place to place on Earth. Let me introduce you again to George and Gracie because they're going to help us think through this. Imagine George and Gracie are sitting in a cafe in our universe having coffee discussing physics. George says to Gracie, "You know, it's remarkable that we're here. I've been reading about how finely tuned the universe is for life. If gravity were just a tiny bit stronger, stars would burn out in millions of years instead of billions, too fast for complex life to evolve. If it were a tiny bit weaker, stars wouldn't form at all. If the electromagnetic force were different by even 1%, chemistry wouldn't work the way it does. Atoms wouldn't be stable. We're incredibly lucky to be in a universe where everything is just right. Gracie responds, well, lucky is one way to put it. But think about it this way. If there are countless bubble universes out there, each with different values for the constants, then of course we find ourselves in one of the rare universes where the constants allow for complexity for stars and planets and life. We couldn't find ourselves in a universe that doesn't allow for observers. It's selection bias on a cosmic scale. George frowns. But that feels like a cop-out. You're saying the universe is the way it is because if it weren't, we wouldn't be here to wonder about it. That's not really an explanation, is it? Gracie shakes her head. I think it is an explanation, just not the kind we're used to. We're used to explanations that say this happens because of that principle. But maybe the real explanation is statistical. Out of 10 to the 500 possible universes, a tiny fraction have the right properties for life. And we find ourselves in one of those because we couldn't exist in any of the others. That's actually quite a profound explanation if you think about it. Now, this is the anthropic principle, and as I mentioned in part 1, it's controversial. Some physicists embrace it enthusiastically. Others hate it with a passion. The critics say it's giving up on finding deeper explanations. They say it's intellectually lazy, that we should keep looking for fundamental principles that determine the laws of physics, not just throw up our hands and say it's this way because we're here. And I understand that criticism. I really do. As a physicist, I want to understand why things are the way they are. I want to find deep principles, elegant symmetries, mathematical necessities. I don't want to just accept that the constants are random accidents. But here's the thing. If the multiverse is real, if eternal inflation really does produce countless universes with different properties, then the anthropic principle isn't giving up on explanation. It's accepting what the theory tells us. The theory says that all these possibilities exist and we necessarily observe one that allows for observers. That is the explanation, even if it's not the kind of explanation we were hoping for. It's like asking, why is Earth habitable? Well, there are billions of planets in our galaxy alone. Most of them are too hot or too cold, too large or too small, orbiting the wrong kind of star at the wrong distance. But we find ourselves on one of the rare planets that's just right for life. Not because Earth is special in some cosmic sense, but because we couldn't have evolved anywhere else. The same logic might apply to the universe as a whole. Of course, and I want to emphasize this, we don't know if the multiverse is real. We don't know if eternal inflation is correct. It's a consequence of taking inflation seriously and following the mathematics. But it might be wrong. There might be mechanisms that shut off inflation globally. There might be selection principles we haven't discovered yet that constrain which vacuum states are actually realized. The final answer isn't settled, and it might not be settled for decades or even centuries. But the mere fact that we can contemplate these possibilities, that we can work out their mathematics and think about their implications, represents a profound expansion of how we think about reality. 100 years ago, the idea of multiple universes was pure science fiction. Today, it's a serious scientific hypothesis that some of the world's best physicists take very seriously. Now let me talk about a very different approach to the before the Big Bang question. This approach takes quantum mechanics seriously at a cosmological scale, and it leads to some really counterintuitive ideas about the nature of time and causation. You're familiar with some of the weirdness of quantum mechanics, right? Particles can be in multiple states simultaneously until you measure them. An electron can be in a superposition of being here and being there, and only when you observe it does it collapse into one definite location. This has been confirmed by countless experiments. The double slit experiment being the most famous. It's not a matter of us not knowing where the electron is. It's genuinely in both places at once until we measure it. Now, quantum mechanics doesn't just apply to particles. It applies to fields, to waves, to anything physical. And in principle, it should apply to the universe as a whole. What if the entire universe, including spacetime itself, is subject to quantum uncertainty? This is the realm of quantum cosmology. And one of its most famous proposals is the Hadar-Hawking no-boundary proposal that I mentioned briefly in part 1. Let me explain it more carefully because it's really quite beautiful, even if it's hard to wrap your mind around. In quantum mechanics, we describe physical systems using something called the wave function. For a particle, the wave function tells you the probability amplitude for finding the particle at different locations. If you square the wave function at a particular point, you get the probability of finding the particle there. The wave function contains all the information about the quantum state of the system. Hadot and Hawking proposed that we should think of the universe as having a wave function, a quantum state that describes all possible configurations of spacetime. Now, this is ambitious. We're not talking about a wave function for particles in spacing. We are talking about a wave function for spacetime itself. Space and time aren't a fixed background. They are dynamical. They can have different shapes and sizes. And the wave function tells us the probability amplitude for each possible spacetime geometry. To calculate this wave function, Hadot and Hawking used a technique from quantum field theory called the path integral. The idea is that you sum over all possible histories, all possible ways the universe could have evolved. And each history contributes to the wave function with a certain amplitude. The paths that minimize a quantity called the axiom contribute the most. Now here's where it gets really interesting. To make the mathematics work, Hadot and Hawking use something called imaginary time or Euclidean time. In ordinary time, what physicists call Lorentzian time, there's a distinction between space and time. Time has a different character. It flows. It has a direction. But in Euclidean time, you treat time as if it were just another dimension of space. You replace the time coordinate with an imaginary number that is a number involving the square root of -1. I know that sounds bizarre. Why would you do that? Well, turns out that when you use Euclidean time, the mathematics becomes much more tractable. You can calculate things that would be impossible in Lorentzian time. And at the end, you can transform back to Lorentzian time to get physical predictions. What Hawking found is that in Euclidean time, the universe can have a geometry that's smooth and closed with no boundary, no edge, no beginning. It's finite in extent, but has no boundary like the surface of a sphere. If you start at any point and move in any direction, you eventually come back to where you started, but you never encounter an edge. And here's the key point in this geometry. There's no moment of creation. There's no first instant of time. Time doesn't begin. It simply is as part of the geometry of the universe. The Big Bang isn't a boundary. It's more like a south pole, a point where certain coordinates converge, but which is perfectly smooth and regular. Think about latitude and longitude on Earth. As you approach the South Pole, the lines of longitude get closer and closer together. And at the South Pole itself, they all meet. But the South Pole isn't special in terms of the geometry. It's just a point on the surface like any other. You can walk right over it without noticing anything unusual. In the same way in the Hadot-Hawking universe, the Big Bang is a point where time converges, but there's nothing singular about it. It's a smooth part of the spacetime geometry. And crucially, you can't go before it. Not because there's a wall or a boundary, but because the concept of before doesn't make sense. It's like asking what's south of the South Pole. The question doesn't have an answer because you've reached the limit of that coordinate system. So in this picture, what existed before the Big Bang? Nothing. But not in the sense of empty space. Nothing in the sense that before doesn't exist as a meaningful concept. Time itself is part of the universe, not something the universe exists in. The universe just is as a complete self-contained four-dimensional geometry with no boundary and no need for an external cause. Now Stephen Hawking used to emphasize this point by asking what lies north of the North Pole, and people would say, well, nothing. That's the northernmost point, and Hawking would say exactly. And in the same way, nothing lies before the Big Bang because that's where time itself begins. But I think the North Pole analogy is actually a bit misleading because it suggests there's still something outside some larger space that the Earth exists in. A better analogy is to say the question itself is malformed. It's asking about a region of spacetime that doesn't exist, not even in principle. Is this picture correct? We don't know. The mathematics is elegant, really beautiful in fact, but it's incredibly hard to test. How do you test a proposal about the quantum state of the entire universe when you only have one universe to observe? However, the no-boundary proposal does make predictions. It predicts a certain spectrum of quantum fluctuations in the early universe, a certain pattern of ripples that should be imprinted on the cosmic microwave background. These predictions are somewhat different from those of other quantum cosmology models. So far, observations are consistent with the no-boundary proposal, but they are also consistent with several competing ideas. We need more precise measurements to really distinguish between them. And we are getting those measurements. The Planck satellite, which operated from 2009 to 2013, gave us incredibly detailed maps of the cosmic microwave background. Future missions and ground-based telescopes are pushing the precision even higher. Every new observation constrains the possibilities, narrows down the range of viable theories. It's slow work, but it's real progress. Let me tell you about yet another idea, one that's quite different from both eternal inflation and the no-boundary proposal. This idea comes from string theory and involves extra dimensions and objects called brains. I've mentioned string theory several times, so let me give you a bit more detail. String theory proposes that the fundamental constituents of nature aren't point-like particles, but tiny one-dimensional strings of energy. These strings can vibrate in different patterns, and each vibration pattern corresponds to a different particle. One pattern gives you an electron, another gives you a quark, another gives you a photon, and so on. It's a bit like how a violin string can vibrate in different modes to produce different musical notes. One of the requirements of string theory is that space must have more than 3 dimensions. Depending on the version of string theory, there might be 9 or 10 dimensions of space. Now, you don't see these extra dimensions in everyday life. So, where are they? The standard answer is that they are compactified, curled up into tiny shapes, so small that we don't notice them. Every point in our familiar 3-dimensional space actually has this extra dimension attached to it, but they are curled up at the Planck scale about 10^35 m, far too small to directly observe. But in the late 1990s, physicists like Lisa Randall and Roman Sundrum explored a different possibility. What if some of the extra dimensions aren't compactified? What if they are actually large, but were confined to a 3-dimensional surface within this higher dimensional space? Imagine you're a flatworm living on a piece of paper. To you, the paper is your entire universe. You can move forward and backward, left and right, but you can't move up or down. You're confined to the 2-dimensional surface of the paper. But the paper itself exists in 3-dimensional space. There's a whole dimension you can't access because you're stuck on the surface. In the brain world scenario, we're like that flatworm. We're confined to a 3-dimensional brain, short for membrane. But this brain exists in a higher dimensional space called the bulk. Everything we're familiar with, matter, light, the forces of nature, is stuck on our brain. We can't escape into the bulk. But gravity, which in general relativity is really the curvature of spacing, can propagate through all the dimensions, including the bulk. Now there might be other brains out there floating in the bulk parallel to ours or at angles to ours. These other brains would be completely separate universes. We couldn't see them. We couldn't interact with them through any force except gravity because all the other forces are confined to our brain. But what if 2 brains collided? What if our brain and another brain came together, smashing into each other with enormous energy? That collision would heat up the brains, creating a hot, dense state of matter and radiation. In other words, it would create a Big Bang. This is the aporeotic scenario developed by Justin Cowrie, Bert Ovart, Paul Steinhardt, Neil Turak, and others in the early 2000s. The word aporeotic comes from the ancient Greek term for a cosmic conflation, a periodic destruction and renewal of the universe. In this picture, our Big Bang wasn't the beginning of time or space. It was a collision between brains in a higher dimensional space that had been there all along. And there's a variant called the cyclic model where this collision isn't a one-time event, but part of an endless cycle. Here's how it works. 2 brains collide, creating our Big Bang. The universe expands and cools. Galaxies form. Stars shine. Planets coalesce. Life emerges. But the brains are attracted to each other by some force, maybe a field in the bulk, maybe the extra-dimensional analog of gravity. Over trillions of years, the expansion of the universe slows and eventually stops. Then it reverses. The brains start approaching each other again. The universe contracts. This is the big crunch. Matter and energy get compressed. Temperatures rise and eventually the brains collide again, producing another Big Bang. And the cycle repeats. Big Bang expansion. Big crunch. Big Bang expansion, big crunch over and over, extending infinitely into the past and infinitely into the future. In this picture, time has no beginning and no end. It's eternal. And our Big Bang is just one beat in an infinite cosmic rhythm. What I find fascinating about the cyclic model is that it addresses a puzzle that's bothered cosmologists for a long time. Why were the initial conditions of our universe so special? Why was everything so smooth and uniform? Why was the temperature so precisely calibrated? In the standard Big Bang picture with inflation, you just have to assume these special initial conditions. You say, well, the inflating field happened to have these properties, but you don't explain why. In the cyclic model, the initial conditions aren't special at all. They are determined by what happened in the previous cycle. The universe went through a big crunch. Everything got squeezed down, and then it bounced back in a new Big Bang. The details from the previous cycle don't survive. They bounce, they get erased, smoothed out. It's a kind of cosmic amnesia. Each cycle starts fresh in a sense with conditions determined by the general dynamics of the contraction and expansion, not by some special fine-tuning. However, the cyclic model has its own challenges. One big issue is entropy. The second law of thermodynamics says that entropy, roughly the amount of disorder in a system, always increases. But if the universe goes through infinite cycles and entropy increases with each cycle, why isn't the universe at maximum entropy already? Why is there still structure, still stars and galaxies, still low entropy configurations that can do interesting things? The cyclic model has responses to this. One idea is that the universe gets bigger with each cycle. So there's always more room for entropy to increase. The entropy does go up, but the maximum possible entropy also goes up. So the universe never reaches maximum entropy. Another idea is that entropy somehow resets during the contraction and bounce. Though exactly how this would work is still being debated. There's also a challenge with the bounce itself. When the universe contracts to a very small size, quantum gravity effects should become important. What happens at the bounce? Does general relativity break down? Do you need a theory of quantum gravity to describe it? And if so, which theory? The cyclic model needs to address these questions, and the answers aren't entirely clear yet. So, like eternal inflation and the no-boundary proposal, the cyclic model is a work in progress. It's a serious idea with real physics behind it, but it's not proven and it might ultimately be wrong. Now, let me tell you about one more wild idea. The notion that the universe might have come from nothing at all. And when I say nothing, I mean literally nothing. No space, no time, no matter, no energy, no laws of physics, just nothing. This sounds crazy, I know. How can you get something from nothing? Doesn't that violate every principle of physics, every intuition we have about cause and effect? But quantum mechanics allows for some very strange things. In quantum field theory, even empty space, the vacuum isn't really empty. It's seething with quantum fluctuations. Virtual particles pop into existence and then annihilate almost immediately. These aren't just mathematical artifacts. They have real measurable effects. The Casimir effect, for instance, is a tiny attractive force between metal plates in a vacuum. And it's caused by these quantum fluctuations of the electromagnetic field. Now, here's a remarkable fact. When you add up all the energy in the universe, all the matter, all the radiation, all the kinetic energy of motion, and then you add in the gravitational potential energy, which is negative, the total might be zero or very close to zero. How can that be? Well, matter and radiation have positive energy, but gravitational fields have negative energy. When you're in a gravitational well like on the surface of the Earth or in orbit around the Sun, you have negative gravitational potential energy. And when you add up all the positive energy and all the negative gravitational energy in the universe, there's a remarkable cancellation. The total energy might be zero. If the total energy of the universe is zero, then creating a universe doesn't violate conservation of energy. You're not getting something from nothing. You're getting positive energy and negative energy that add up to nothing. It's like borrowing money from one account and depositing it in another. Your total balance hasn't changed. So the idea proposed by physicists like Alexander Verne and others is that the universe could have emerged as a quantum fluctuation from literally nothing. In quantum mechanics, there's a process called quantum tunneling where a particle can suddenly appear on the other side of a barrier even if it doesn't have enough energy to classically go over the barrier. It's as if the particle tunnels through the barrier appearing on the other side without ever being in between. De Lincoln proposed that the universe itself could have tunneled into existence from nothing. One moment there's no space, no time, no anything. The next moment though, moment isn't really the right word because time itself is created. There's a tiny quantum universe perhaps with the inflating field already in place. Then inflation kicks in. The universe expands rapidly and you get the Big Bang and everything that follows. Now I want to be really clear about the speculative nature of this idea. We don't have a complete theory of quantum gravity. So we can't calculate this process rigorously. We're extrapolating quantum mechanics and general relativity into a regime where neither theory is fully reliable. But what I find fascinating is that we can even contemplate such ideas mathematically. A century ago, this would have been pure philosophy or theology. Today, it's theoretical physics that might someday be testable. Of course, you might object, if the universe came from nothing, what determined the laws of physics, what determined that quantum mechanics and general relativity apply? And do something rather than nothing. And that's a fair point. When we say nothing, we still mean a kind of nothing governed by mathematical laws. We're not explaining where the laws themselves come from. Some physicists like Max Tegmark take this even further. Tegmark proposes that mathematics is reality. That every mathematically consistent structure exists in some sense and our universe is just one of those structures. The laws of physics aren't imposed from outside. They are the mathematics of our particular structure. In this view, there isn't something rather than nothing. There's everything. Every possible universe exists, and we find ourselves in one of them. It's a bold idea, almost metaphysical in its scope, and it raises as many questions as it answers. But it shows how deeply physicists are thinking about these issues. Now, let me step back and talk about what all of these scenarios tell us about the nature of time. Because whether it's eternal inflation, the no-boundary proposal, the cyclic model, or quantum creation from nothing, they all challenge our conventional understanding of time. In eternal inflation, time doesn't have a global beginning. Each bubble universe has its own time that starts with its Big Bang. But the eternally inflating background has been going on forever. Time in the multiverse is infinite. Even though time in our universe has a finite age in the no-boundary proposal, time emerges from a timeless quantum state. There's no moment of creation, no first instant. Time just is as part of the geometry of the universe. The concept of before the Big Bang doesn't apply because before assumes a time coordinate that doesn't extend that far. In the cyclic model, time is eternal in both directions. There's no beginning and no end, just an endless sequence of expansions and contractions. Our Big Bang is one event in an infinite chain. And in quantum creation from nothing, time itself is created along with space and matter. There's no pre-existing time in which the creation event occurs. Time starts at the moment of creation and there's no before. These different pictures of time are profoundly different from each other and they are all different from our everyday experience of time as an ever-flowing river carrying us from past to future. They suggest that time might not be as fundamental as we think. It might be emergent arising from some deeper structure that isn't itself temporal. This is an idea that's taken very seriously in quantum gravity research. In some approaches to quantum gravity like loop quantum gravity or causal set theory, time is not a fundamental feature of reality. It emerges from something more primitive. Maybe a network of causal relationships, maybe a discrete structure of quantum events. At the most fundamental level, there might not be time at all, just a web of connections and relationships from which our experience of time emerges at larger scales. It's a bit like temperature. Temperature is a property of collections of particles. It's the average kinetic energy of the particles in a substance. But individual particles don't have temperature. Temperature is an emergent property that only makes sense when you have many particles. Maybe time is like that, a property that emerges when you have many quantum degrees of freedom, but not a property of the fundamental description of reality. If that's true, then asking what existed before the Big Bang might be like asking what's the temperature of a single atom. The question assumes a concept time in this case that only applies in certain contexts. At the most fundamental level where quantum gravity reigns, time might not exist. And if time doesn't exist, then before doesn't have meaning. Now, let me bring George and Gracie back to explore what all of this means for the concept of causation. They are sitting in that same cafe having finished their coffee and they are deep in conversation. George says, "Okay, so let me see if I understand this. In some of these theories, like the no-boundary proposal, time itself begins at the Big Bang. There's no before. But doesn't that mean the Big Bang has no cause? Doesn't everything need a cause?" Gracie considers this. Well, that's the question, isn't it? In our everyday experience, everything has a cause. You drop a glass and it breaks. The cause is you're dropping it, but causation requires time. You need a before and an after. The cause comes before the effect. So, if time itself begins at the Big Bang, then the Big Bang can't have a cause in the conventional sense. Asking for the cause of the Big Bang would be like asking for the cause of time itself. George frowns, but that's so unsatisfying. It feels like we're just giving up on explanation. Gracie shakes her head. I don't think we're giving up. I think we're recognizing that our concepts like cause and before might not apply at the most fundamental level. It's like asking what's north of the North Pole. The question feels like it should have an answer, but it doesn't because north doesn't apply at the North Pole. Maybe cause doesn't apply at the Big Bang. George isn't entirely convinced. But what about the other theories like eternal inflation or the cyclic model in those time does extend before the Big Bang? So what caused our Big Bang in those scenarios? Gracie nods. In eternal inflation, our Big Bang was caused by the end of inflation in our region. The important field decayed. Its energy converted to matter and radiation. And that's what we call the Big Bang. So there is a cause, but it's not a first cause. It's just one event in a much longer chain. And the cyclic model. In the cyclic model, our Big Bang was caused by the collision of branes or by the bounce from a previous contraction. Again, there's a cause, but it's not a first cause. The chain of causation extends infinitely into the past. George leans back in his chair. So, in some theories, the Big Bang has no cause because causation doesn't apply. In other theories, the Big Bang has a cause, but the chain of causation goes back forever. Either way, we never get to a first cause, a prime mover, an ultimate explanation. Gracie smiles. That's about right. And maybe that's just how reality is. Maybe at some point you either have to accept an infinite regress of causes or you have to accept that causation itself is an emergent concept that doesn't apply at the most fundamental level. I think Gracie is right. This is one of those deep questions where any answer is going to violate our intuitions. Either causation extends infinitely into the past or it has a beginning or it's emergent. None of these options feel comfortable, but one of them must be true. And you know, this is a place where physics and philosophy meet. Physics can tell us what the laws of nature are, how things evolve, what the structure of spacing is, but whether every event must have a cause, whether infinite regress is acceptable, whether existence itself requires an explanation, these are questions that straddle the boundary between physics and metaphysics. As a physicist, I'm comfortable saying, here are the possibilities that our current theories suggest. Here are the observations that constrain them. Here's what we need to learn to decide between them. But I'm also humble enough to recognize that there might be limits to what physics can tell us. Some questions might be forever beyond the reach of empirical science. That said, I'm optimistic that we'll make progress. Every decade, our observations get more precise, our theories get more refined, our understanding deepens. We've learned things about the universe that our grandparents couldn't have imagined. And I believe future generations will learn things we can't imagine today. In part 3, we're going to bring all of this together. We are going to explore what these different scenarios mean for the biggest questions of all. Why is there something rather than nothing? What is the ultimate nature of reality? And what does our place in the cosmos look like if we live in an eternal multiverse, or if our universe emerged from nothing, or if time itself is an illusion? Because this isn't just about cosmology. It's about understanding our place in the grand scheme of things. It's about the meaning of existence, the nature of time, the limits of knowledge. These are the deepest questions humans have ever asked. And for the first time in history, we have the tools to make real progress on them. So in part 3, we'll explore the philosophical and existential implications of what we've learned. We'll think about what it means for consciousness to arise in a universe that might be one of infinitely many, or that might have emerged from nothing. We'll consider whether science can ever truly answer the question, why is there something rather than nothing? And we'll reflect on the extraordinary fact that we finite beings with finite lifespans can even contemplate these cosmic mysteries. The journey we've been on is a journey to the edge of knowledge, to the boundary of what physics can tell us about reality. And at that boundary, we find not emptiness but profound mystery. The kind of mystery that makes you pause and think what an extraordinary universe we live in, and what an extraordinary thing it is to be alive, to be conscious, to be able to ask these questions. So, here we are at the final stage of this journey into one of the deepest questions we can ask. What existed before the Big Bang? We've traveled through the well-established science of cosmic evolution, ventured into the speculative frontiers of eternal inflation and quantum cosmology, explored cyclic universes and brane collisions. And now I want to step back and think about what all of this means, not just for physics, but for how we understand reality, existence, and our place in the cosmos. Because the question, what existed before the Big Bang, isn't just a technical question about cosmology. It's a question that touches on profound philosophical issues that humans have grappled with for millennia. The nature of time, the meaning of causation, the possibility of creation from nothing, why there's something rather than nothing, and what it means for us finite beings with finite lifespans living on a small planet orbiting an ordinary star in an unremarkable galaxy to be part of this enormous, possibly eternal cosmos. Let me start with time, because I think understanding what modern physics tells us about time is crucial for making sense of everything else. We experience time as a flow, as a river carrying us inexorably from past to future. We remember yesterday. We live in the present. We anticipate tomorrow. This experience is so fundamental to how we navigate the world that it's hard to question it. Time just seems obviously real, obviously flowing, obviously fundamental. But physics has been questioning this intuitive picture of time for more than a century now. And the answers we've gotten are strange. Einstein's special relativity taught us that time isn't absolute. That different observers moving at different speeds will disagree about the duration between events, about which events are simultaneous, even about the order of events in certain cases. Time, it turns out, is relative. It depends on your motion. General relativity went even further. It told us that time and space are woven together into a single fabric spacing. And that this fabric can stretch and warp and curve. Time can dilate, can slow down near a massive object or at high speeds. Near the event horizon of a black hole, time slows to a crawl compared to someone far away. There's no universal clock ticking away the same seconds for everyone everywhere. Time is local, personal, observer-dependent. But even with all of that weirdness, there was still a notion of time in physics. There was still a parameter labeled t that appeared in the equations. There was still a sense in which you could say this happened and then that happened. Events had a temporal ordering even if different observers disagreed about the details. What quantum cosmology and the ideas we've been exploring are telling us is that even that might be too restrictive. Time itself might not be fundamental. It might be something that emerges only in certain contexts, at certain scales, in certain regimes of the universe's evolution. Think about what happens at the very beginning in the Plon epoch. Those first 10⁻⁻43 seconds after the Big Bang. At that scale, quantum gravity effects dominate. The universe is so small, so dense, so energetic that the usual rules break down. Space and time as we know them might not even exist in that regime. The smooth continuous spacetime of general relativity gives way to something quantum, something discrete, something that doesn't have the properties we normally associate with time. In some approaches to quantum gravity, like loop quantum gravity, spacetime is fundamentally granular. It's made up of discrete units, quantum building blocks. At the Planck scale, there might not be a smooth flow of time. There might be a kind of quantum foam where space and time fluctuate and bubble and don't have definite values in that regime. Asking what happened before might not make sense because there's no clear temporal ordering. There's no before and after in the way we usually think about it. And in the hard-Hawking no-boundary proposal, you have this picture where time emerges smoothly from a state that's fundamentally timeless. In their mathematical formulation, they use Euclidean time where the distinction between space and time disappears. It's all just geometry. And then as you move away from the Big Bang, as the universe gets bigger and cooler, Euclidean time transitions to Lorentzian time, the time we're familiar with, the time that flows and has a direction. So time in this view isn't a fundamental feature of reality that exists eternally and independently. It's an emergent feature that arises in certain contexts. It's a bit like temperature. Temperature is a useful concept when you're talking about a cup of coffee or a pot of water. It tells you about the average kinetic energy of the molecules. But an individual molecule doesn't have a temperature. Temperature is a statistical property that only makes sense when you have many particles. It emerges from the collective behavior of the system. Maybe time is like that. Maybe at the most fundamental level of reality, whatever that is, there's no time. There's just some quantum state, some configuration of fundamental degrees of freedom. And then when you zoom out, when you look at the system at larger scales with many degrees of freedom, time emerges as a useful way to organize our observations and predictions. It's not fundamental. It's emergent. If that's true, and I want to emphasize, we don't know if it's true, but it's a serious possibility, then the question, what existed before the Big Bang, is based on a flawed assumption. It assumes that time extends infinitely into the past, that there's always a before for any moment. But if time itself began at the Big Bang, or if time is something that only makes sense within our cosmic bubble, or if time is emergent from a timeless quantum state, then there simply is no before in the conventional sense. Now, I know that's deeply unsatisfying to some people. It feels like we're dodging the question, like we're playing word games. You're just saying the question doesn't make sense instead of answering it. And I understand that frustration. But I don't think we're dodging the question. I think we're recognizing that the question as formulated in our everyday language doesn't map onto the structure of reality at the most fundamental level. It's genuinely like asking what's north of the North Pole. The question makes grammatical sense. We understand all the words. We can parse the sentence structure, but it doesn't make geographical sense because north is defined relative to the North Pole. Once you're at the North Pole, north doesn't point anywhere. The concept doesn't apply. In the same way, before is defined relative to a time coordinate. And if that time coordinate doesn't extend past the Big Bang either because it begins there or because it's emergent and only applies in certain regimes, then before the Big Bang doesn't point to anything. The concept doesn't apply. But, and this is important, there are other scenarios where time does extend beyond the Big Bang. In eternal inflation, time doesn't have a global beginning. Each bubble universe has its own time that starts with its Big Bang. But the eternally inflating background has been going on for much longer, maybe forever. Time in the multiverse is infinite. Even though time in our universe has a finite age, in the cyclic model, time is eternal in both directions. There's no beginning and no end, just an endless sequence of expansions and contractions, big bangs and big crunches. Our Big Bang is one beat in an infinite cosmic rhythm that's been going on forever and will continue forever. So depending on which theory is correct, the nature of time could be radically different. And we don't know yet which picture is right. We might not know for a long time, but the very fact that we can contemplate these different possibilities, that we can work out their mathematical implications and think about how to test them, that represents an extraordinary expansion of human understanding. A few hundred years ago, time was just time. It was obvious, unchanging, absolute. Newton thought of time as flowing uniformly, independent of anything else. Now we know it's relative. It's curved. It might be emergent. It might have a beginning or it might be eternal. That's progress. That's how science works. We question assumptions that seemed unquestionable. We follow the mathematics where it leads. We look at the universe and let it tell us about its own nature, even when that nature is stranger than we imagined. Let me talk about causation now because that's intimately connected to time. In our everyday experience, causation has a clear direction. Causes breed effects. You flip a light switch and then the light turns on. You drop a glass and then it breaks. You don't see a broken glass spontaneously assembling itself and jumping back onto the table. Time moves forward and causation moves forward with it. The past determines the future, not the other way around. But at a fundamental level, the laws of physics don't distinguish between past and future. If you watch a movie of planets orbiting the sun or of billiard balls colliding on a pool table, you can't tell if the movie is playing forward or backward. The laws of motion work the same either way. This is called time reversal symmetry and it holds for most fundamental interactions in physics. So where does the arrow of time come from? Why does causation have a direction? Why do we remember the past but not the future? Why does entropy, the amount of disorder in a system, always increase? The answer, physicists believe, has to do with the initial conditions of the universe. The Big Bang created a state of incredibly low entropy. Everything was smooth and uniform. All the energy was concentrated in a small region. And that's a very special, very low entropy configuration. And the second law of thermodynamics says that entropy tends to increase over time. So as the universe evolves, it moves from this low entropy initial state to higher and higher entropy states. Structure forms galaxies, stars, planets. And that might seem like entropy is decreasing because structure is more organized than uniformity. But actually the formation of structure increases the total entropy when you account for all the heat and radiation that's released in the process. Stars burn hydrogen into helium, releasing photons that spread out and increase entropy. Life emerges and maintains itself by consuming low entropy energy sources and releasing high entropy waste heat. The net effect is always an increase in entropy, and that increase in entropy gives us the arrow of time. It defines a direction, a flow from low entropy to high entropy, from past to future. We remember the past because memories are low entropy records, and we can't remember the future because high entropy states don't contain information about their low entropy past in an easily accessible way. But this raises a puzzle. Why was the entropy so low at the Big Bang? Why did the universe start in such a special fine-tuned state? This is called the past hypothesis or the initial condition problem, and it's one of the deep mysteries of cosmology. One answer which I've mentioned is that maybe it didn't start that way. Maybe in the cyclic model the low entropy of our Big Bang was the result of processes in the previous cycle that reset or reorganized the entropy. Or maybe in eternal inflation, the low entropy is just a statistical fluctuation, one that's necessary for our existence. So we shouldn't be surprised to find ourselves in such a universe. It's anthropic selection. Again, another answer is that maybe we're thinking about it wrong. Maybe the low entropy of the Big Bang is a consequence of the laws of quantum gravity, something that's required by the deeper structure of reality. In the Hartland-Hawking no-boundary proposal, for instance, the smooth closed geometry naturally gives you low entropy at the Big Bang. It's not fine-tuned. It's a natural consequence of the mathematics. We don't know yet which answer is right. But here's what I want to emphasize. The question what caused the Big Bang might be subtly malformed. It assumes that causation, the familiar notion of one event leading to another, extends all the way back to the beginning. But if time itself began at the Big Bang, then there's no before for a cause to exist in. The Big Bang wouldn't have a cause in the conventional sense because causation requires time and time begins with the Big Bang. Or if time is eternal, as in some models, then maybe the chain of causation extends infinitely into the past. Every event has a cause. But there's no first cause, no prime mover. The universe is just an eternal dance of cause and effect with no beginning and no end. Or in the quantum picture, maybe causation itself breaks down at the fundamental level. You know, quantum events like the decay of a radioactive nucleus or the tunneling of a particle through a barrier don't have causes in the classical sense. They just happen probabilistically. You can calculate the probability that a uranium atom will decay in the next second, but you can't say what causes a particular atom to decay at a particular moment. It's genuinely random, genuinely uncaused. And if the universe itself is a quantum event, a quantum fluctuation or a quantum tunneling from nothing into something, then it doesn't have a cause in the classical sense. It's just a probabilistic occurrence in the quantum realm. The universe happens because quantum mechanics allows it to happen, not because something caused it to happen. Each of these possibilities challenges our intuitions about how reality should work. But that's okay. Our intuitions evolved to help us survive on the African savanna to navigate a world of medium-sized objects moving at medium speeds in weak gravitational fields. Our intuitions didn't evolve to understand the origin of the cosmos, the nature of quantum gravity, the structure of spacetime at the Planck scale. So when our intuitions fail us at these extremes, that's not a sign that we're doing something wrong. It's a sign that we're pushing into territory our ancestors never needed to navigate. Now, let me talk about the question that I think haunts this whole discussion. The question that philosophers have been asking for millennia. Why is there something rather than nothing? This question has been posed by philosophers and theologians throughout history. Linnaeus posed it as a fundamental metaphysical question. Why is there something rather than nothing? Heidegger called it the most important question in philosophy. And it's a question that physics, with all its success at describing how things work, hasn't really answered. We can describe how the universe evolved from the Big Bang. We can even propose mechanisms by which the universe might have come into existence. Quantum fluctuations, colliding brains, eternal inflation, whatever. But those mechanisms themselves presuppose the existence of something. Quantum fields, extra dimensions, the laws of physics, the mathematical structures that describe reality. So why do those things exist? Why is there a quantum field capable of fluctuating? Why are there laws of physics at all? Why is there a mathematical framework that describes reality? Why does mathematics work so unreasonably well at describing the physical world, as the physicist Eugene Wigner famously asked? Some physicists like Max Tegmark have proposed a radical answer. Tegmark suggests that mathematics is reality, that every mathematically consistent structure exists in some sense and our universe is just one of those structures. In this view, the question why is there something rather than nothing is answered by saying there isn't just something, there's everything. Every possible universe, every possible mathematical structure exists. And we find ourselves in one of them because we're part of that structure. It's a bold idea and it has some appeal. It would explain why the laws of physics are mathematical. They are not just described by mathematics. They are mathematics. There's no distinction between the physical and the mathematical. And it would explain why our universe has the properties it does, because all possible universes exist and we necessarily find ourselves in one that allows for our existence. It's the ultimate anthropic principle. But it also raises as many questions as it answers. Why should mathematical structures exist? What does it mean for a mathematical structure to exist if there's no physical reality instantiating it? Is mathematics discovered or invented? And if every possible universe exists, is that really an explanation, or is it just saying everything happens without explaining why anything happens at all? Other physicists are more cautious. They say that physics can describe how things work and how they evolve, but it can't explain why there's something rather than nothing. That question, they say, is beyond the scope of science. It's a question for philosophy or theology, or maybe a question that simply has no answer. Maybe existence is a brute fact, something we just have to accept without explanation. My own view is that we should be humble about what we can and can't explain. Physics has done remarkably well at explaining the how of the universe. We understand in broad strokes how stars shine, how galaxies form, how atoms bond, how planets coalesce, how life evolves. We've traced the history of the universe back to a fraction of a second after the Big Bang. We can describe the evolution of the cosmos from a hot dense plasma to the vast cool expanse we see today, filled with hundreds of billions of galaxies, each with hundreds of billions of stars. But the why questions, why these laws rather than others, why these constants rather than others, why existence rather than non-existence, those might require a different kind of explanation. Or they might not have explanations in the way we typically think about explanations. They might be brute facts about reality that we simply have to accept. And you know what? I think there's a kind of beauty in that. If we could explain everything, if there were no ultimate mysteries, if we could derive the existence of the universe from some logical necessity, reality would be less wondrous. It would be less surprising. The fact that we can ask questions that might have no answers, that we can contemplate mysteries that might be eternal, that's part of what makes us human. It's part of what makes the pursuit of understanding so compelling and so meaningful. Let me bring George and Gracie back one more time because I want to use them to explore how all of this affects our sense of meaning and purpose. Imagine they're sitting on their porch at night looking up at the stars. They've been thinking about everything we've discussed, the Big Bang, the multiverse, the possibility that time had a beginning or that it's eternal. The idea that our universe might be one bubble in an infinite froth of universes. The notion that existence itself might be a quantum accident. George says, "You know, when I think about all of this, it makes me feel small, insignificant, even if our universe is just one of countless universes. If the Big Bang that created everything we know was just a random event in some vaster reality. If even the laws of physics are just accidents of how things happen to settle in our region of space, then what's special about us? What's special about anything we do? What does it matter if we love or hate, create or destroy, succeed or fail? We're just tiny specks in an infinite cosmos. Here for a brief moment and then gone forever." Gracie is quiet for a moment, looking up at the stars. Then she says, "I see it differently. Yes, we are tiny in space and time. Yes, there might be countless other universes out there. And yes, we're just a brief flicker in cosmic history, but so what? Does that make our experiences any less real? Does that make love or beauty or curiosity or wonder any less meaningful? Does the existence of other planets make Earth less special to us? Does the existence of other people make you less special to me?" She continues, "Think about it this way. The fact that the universe is so vast, so ancient, so full of mysteries we're only beginning to understand that makes it more amazing that we're here to think about it, not less. We're made of atoms forged in stars billions of years ago. We are connected to the origin of the universe in a physical literal way. The carbon in our bodies, the oxygen we breathe, the calcium in our bones, all of it was created in stellar furnaces and scattered into space by supernova explosions. We are quite literally made of stardust." George nods slowly. "I've heard that before. Carl Sean said it right. We are made of star stuff." Exactly. And not only are we made of the universe, but through us, the universe has become aware of itself. Think about that. For billions of years, matter existed, but didn't know it existed. Stars burned, galaxies formed, planets cooled, but there was no consciousness, no awareness, no understanding. And then on at least one planet orbiting one star in one galaxy, complexity increased to the point where matter became conscious, where the universe opened its eyes, so to speak, and began to look at itself. George considers this, and we've developed the ability to understand the universe, to look back through time to see the cosmic microwave background, to understand how the universe evolved, to ask questions about what came before the Big Bang, right? And that's extraordinary. There are, as far as we know, only a few species on one planet in one galaxy in one universe that can do this. Maybe we're common in the cosmos. Maybe we're rare. We don't know yet. But either way, we're special. We're the universe's way of understanding itself, of reflecting on its own existence and origin." George smiles. "So, you're saying that even if we're tiny and brief, even if we're just one possibility among infinite possibilities, even if our universe is just one bubble in an eternal multiverse, even then we matter. Because we're the part that knows, that understands, that cares." Exactly. Meaning isn't something imposed from outside. It's something we create, something we experience. The fact that the universe is large doesn't make us small in any way that matters. The fact that time is long doesn't make our lives short in any way that matters. We are here. We are conscious. We can think and feel and wonder and love. That's what matters. I think Gracie is right. The question of whether our universe is unique or one among many is a factual question about the structure of reality. But questions about meaning and significance, those are human questions. They're about what matters to us, about what we value, about how we choose to live our lives and relate to each other and engage with the world. And here's what I believe. The fact that we can even ask these questions, the fact that we can probe the origins of the universe and contemplate the nature of time and existence and think about what came before the Big Bang. That's remarkable. That's profound. That's a reason for awe and wonder, not for despair or nihilism. Carl Schurz said it beautifully. We are a way for the cosmos to know itself. We are not separate from the universe looking at it from the outside. We are part of it. We are made of it. We are expressions of it. And through us, the universe is able to reflect on its own nature, to marvel at its own existence, to ask deep questions about its own origin and ultimate fate. That's not diminished by the universe being large or old or having other universes alongside it. If anything, it's enhanced. The bigger and stranger and more wonderful the universe turns out to be, the more remarkable it is that we're here to appreciate it, to understand it, to be astonished by it. Now let me talk about where this research is heading, because I think that's important for understanding where we are in this grand quest to understand our cosmic origins. First, observations. Every year our telescopes get more powerful, our detectors get more sensitive. Our observational techniques get more sophisticated. We are building instruments that can measure the cosmic microwave background with exquisite precision, looking for patterns that could tell us about inflation, about quantum fluctuations in the early universe, about the nature of space and time at the Planck scale. We are detecting gravitational waves now, ripples in spacetime from colliding black holes and neutron stars. The first detection by LIGO in 2015 opened up a completely new way of observing the universe. And we're working on more sensitive detectors that could potentially see gravitational waves from the early universe from cosmic inflation itself. If we could do that, we'd be looking back to an incredibly tiny fraction of a second after the Big Bang, to a time when the universe was so hot and dense that our current theories are barely adequate to describe it. We are mapping the distribution of galaxies across billions of light years, looking for patterns that could tell us about the initial conditions of the universe, about the nature of dark energy, about whether there are any signatures of a multiverse in the large-scale structure of the cosmos. Projects like the Sloan Digital Sky Survey and its successors have mapped millions of galaxies, and we are finding subtle patterns that constrain our theories. We are studying the cosmic microwave background with incredible precision. The Planck satellite gave us temperature maps accurate to millionth of a degree. We are now looking for even subtler effects. The polarization of the microwave background, which could tell us about gravitational waves from inflation. We are looking for non-Gaussianities, which are deviations from perfect randomness in the temperature fluctuations that could tell us about the physics of inflation. Every new observation constrains the possibilities, narrows down the range of viable theories. It's slow work, painstaking work, but it's real progress. We're not just speculating anymore. We are testing our ideas against reality. Second, theory. Physicists are working hard on quantum gravity, trying to unify general relativity and quantum mechanics into a single consistent framework. String theory is one approach with its vibrating strings and extra dimensions. Loop quantum gravity is another with its discrete granular spacetime. There's causal set theory, which treats spacetime as fundamentally discrete, made up of elementary events. There are approaches based on holography, on the idea that the information content of a region of space is encoded on its boundary. We don't know which, if any, of these approaches will prove correct. But the process of developing these theories is teaching us new mathematics, new ways of thinking about space and time and matter and energy. We are learning that spacetime might be emergent, arising from something more fundamental, maybe quantum entanglement, maybe information, maybe some structure we haven't fully grasped yet. We are also doing computer simulations, running virtual universes on supercomputers to see how structure forms, how galaxies evolve, how the cosmos would look under different assumptions about the laws of physics and the initial conditions. These simulations help us understand what we should expect to observe if different theories are correct. And third, experiments. We are building particle accelerators to probe higher and higher energies, trying to find new particles or new forces that could tell us about how the laws of physics change in extreme conditions. The Large Hadron Collider at CERN has discovered the Higgs boson, confirming a key prediction of the Standard Model. But we are also looking for physics beyond the Standard Model. Supersymmetry, extra dimensions, dark matter particles, anything that could give us a clue about the deeper structure of reality. So far, we haven't found anything beyond the standard model. No supersymmetric particles, no signs of extra dimensions, no direct detection of dark matter particles. But we keep looking because we know the standard model isn't complete. It doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't tell us why the parameters have the values they do. All of this work, observations, theory, experiments is slowly constraining the possibilities. It's helping us figure out which ideas are viable and which aren't. It's a slow process, frustratingly slow sometimes, and there are no guarantees. We might not get definitive answers in our lifetimes, but we are making progress. Step by step, observation by observation, calculation by calculation. And every once in a while, we get a surprise. We discover dark energy accelerating the expansion of the universe when we expected it to be slowing down. We detect gravitational waves, opening up a completely new window on the cosmos. We find galaxies that formed earlier than we thought possible, challenging our models of structure formation. And those surprises often open up new questions, new avenues of research, new mysteries to explore. That's the nature of science at the frontier. It's not a steady march toward complete knowledge. It's more like exploring a vast landscape where each hill you climb reveals more hills beyond, where each question you answer raises new questions you hadn't thought to ask. It's messy and uncertain and full of dead ends and false starts. But it's also exhilarating and profound and deeply meaningful. Now I want to return to where we started the Big Bang and the question of what came before. We began with the observable facts, the expansion of the universe, the cosmic microwave background, the abundances of light elements. These facts are well established, confirmed by multiple lines of evidence. The Big Bang theory in its broad strokes is as well confirmed as any theory in science. But the Big Bang theory is a description of how the universe evolved from a hot, dense state 13.8 billion years ago. It's not a theory of the ultimate origin. It doesn't tell us what caused the Big Bang or what, if anything, came before or why there's a universe at all rather than nothing. For those deeper questions, we've ventured into more speculative territory. We've explored ideas like eternal inflation, which suggest our Big Bang was just one of many in a vast, possibly infinite multiverse. We've considered the Hadal-Hawking no-boundary proposal, which suggests time itself emerged from a quantum state and has no meaningful before. We've looked at the cyclic model where Big Bangs and Big Crunches repeat eternally. We've thought about quantum creation from nothing, where the universe tunnels into existence as a quantum fluctuation. We've contemplated brane collisions in higher dimensional spaces. Each of these ideas is a serious scientific proposal based on extensions of well-tested theories like general relativity and quantum mechanics. But none of them has been proven. We don't know which, if any, is correct. And it's possible that the true answer is something we haven't thought of yet. Something that will seem obvious once we have a complete theory of quantum gravity, but that eludes us. Now, what I hope you take away from this is not a definite answer because I can't give you one, but an appreciation for how deep the question goes and how hard physicists are working to answer it. The question, what existed before the Big Bang, is not just a question about the past. It's a question about the nature of time itself, the meaning of causation, the structure of reality, the ultimate origin of everything. It's a question that touches on physics and philosophy, on science and metaphysics, on what we can know and what might be forever beyond our reach. And yet, we are making progress. We're developing theories, working out their implications, looking for ways to test them. We're building telescopes and detectors and accelerators. We are observing the universe with ever greater precision. And occasionally, we find something that surprises us, that constrains our theories, that points us in a new direction. This is how science works at the frontier. It's uncertain and challenging and sometimes frustrating, but it's also exhilarating and profound and deeply meaningful because we're not just gathering facts. We're trying to understand the deepest truths about reality. We are asking questions that humans have wondered about for millennia, and for the first time in history we have the tools, mathematical, observational, experimental, to make real progress on them. So when someone asks me what existed before the Big Bang, I don't say I don't know with resignation or frustration. I say I don't know with excitement and anticipation because it's one of the great mysteries, one of the profound questions that we are actively working on. There's nothing more thrilling than being part of that quest of pushing the boundaries of human knowledge, of trying to understand the universe at its most fundamental level. You know, when I started studying physics, the Big Bang theory was still somewhat controversial. Some respected physicists preferred the steady-state model, which held that the universe had no beginning and was eternal and unchanging on large scales, with new matter continuously being created to maintain constant density as the universe expanded. The discovery of the cosmic microwave background in 1965 by Penzias and Wilson pretty much settled that debate in favor of the Big Bang. The steady-state model couldn't explain the microwave background, but the Big Bang predicted it. But in winning that battle, we opened up a new frontier. The question shifted from did the universe have a beginning to what happened at that beginning and what if anything came before. And that's where we are now. We are exploring that frontier and we are finding it even stranger and more wonderful than we imagined. So I think in a way that's the story of physics over the last century. Every time we answer a question we find deeper questions beneath. We thought atoms were the smallest particles. Turns out they are made of protons, neutrons, and electrons. We thought protons and neutrons were fundamental. Turns out they are made of quarks held together by gluons. We thought space and time were fixed and absolute. Turns out they are relative and curved and woven together into a single fabric. We thought the universe was static. Turns out it's expanding. And that expansion is accelerating due to dark energy. Each discovery reveals more complexity, more structure, more mystery. And the question of what existed before the Big Bang is the latest chapter in that story. It's the question that emerges when you push our current understanding to its limits and ask what lies beyond. Will we answer it? Maybe, maybe not. But we'll try. And in trying, we'll learn things we can't even imagine yet. We'll develop new mathematics, new observational techniques, new ways of thinking about reality. And even if we don't get the final answer, we'll get closer. We'll narrow down the possibilities. We rule out some ideas and gain confidence in others. And that's worth doing. Not just because the answer matters, though it does, but because the pursuit of understanding is one of the most human things we can do. It's what separates us from other animals. It's what has driven our progress from caves to cities, from superstition to science, from ignorance to enlightenment, from wondering at the stars to walking on the moon to peering back to the first moments after the Big Bang. So, here we are, standing on this small planet, orbiting an average star in an ordinary galaxy, looking out at a cosmos that contains hundreds of billions of galaxies, each with hundreds of billions of stars spanning nearly 14 billion years of cosmic history. And we are asking, where did all this come from? What existed before the beginning? Why is there something rather than nothing? And the remarkable thing is that we have the tools, mathematical, observational, experimental, to make real progress on these questions. We're not just philosophizing in armchairs, though there's certainly a place for philosophy in this discussion. We are doing science. We are proposing theories based on well-established physics, testing them against observations, refining them when they fail, celebrating when they succeed. We are observing the universe with incredible instruments and letting it tell us about its own nature. That's an extraordinary privilege. And it's an extraordinary responsibility because we're the ones asking these questions on behalf of all humanity, on behalf of all conscious beings in our universe. We're the ones pushing the boundaries of knowledge, exploring the frontiers of understanding, trying to figure out how reality works at its most fundamental level. And when we find answers, or even when we make progress toward answers, we are adding to the collective knowledge of our species. We are contributing to a tradition that stretches back thousands of years to the first humans who looked up at the stars and wondered what they were. To the ancient Greeks who asked about the nature of matter in motion, to Copernicus and Galileo who challenged the geocentric model. To Newton who unified terrestrial and celestial mechanics, to Einstein who revolutionized our understanding of space and time, to Hubble who discovered the expansion of the universe. We are part of that grand human project of understanding the cosmos. And the question of what existed before the Big Bang is one of the latest and most profound chapters in that project. So let me leave you with this. The universe is vast and ancient and strange and wonderful. It's governed by laws we're still working out, shaped by events we're still trying to understand. It might be one of infinitely many universes. It might have emerged from nothing. Time itself might have begun with the Big Bang, or it might be eternal. We don't know yet. But we tiny, finite, ephemeral beings that we are have the capacity to probe these deepest mysteries. We can look back through time to see the universe as it was when it was only 380,000 years old. We can detect gravitational waves from black holes colliding billions of light years away. We can calculate what should have happened in the first fraction of a second after the Big Bang and then check our calculations against observations. We can contemplate the nature of time itself, the meaning of causation, the possibility of creation from nothing. That should fill you with awe. It should make you appreciate how remarkable it is that we exist, that we're conscious, that we can think and wonder and ask questions about the nature of reality. The atoms in our bodies were forged in the nuclear furnaces of stars. We are connected to the cosmos in the most direct possible way. We are literally and physically children of the stars, product of 13.8 billion years of cosmic evolution. And through us, the universe is coming to understand itself. Through our telescopes and equations and experiments, through our theories and observations and imagination, the cosmos is reflecting on its own nature, its own origin, its own ultimate fate. For billions of years, the universe existed but didn't know it existed. Galaxies formed, stars burned, planets cooled, but there was no consciousness, no awareness. And then, at least here on Earth, complexity increased to the point where matter became conscious, where the universe opened its eyes and began to look at itself. That's not a small thing. That's not insignificant. That's profound. And regardless of how vast the universe is, regardless of whether there are other universes beyond ours, regardless of whether the Big Bang was a beginning or just one event in an eternal sequence, regardless of all that, the fact that we're here thinking about these questions, trying to understand where we came from and why we exist, that's one of the most remarkable things in all of reality. So, keep wondering. Keep asking questions. Keep looking up at the stars and thinking about what they tell us about our origins. Don't let anyone tell you these questions don't matter or that we shouldn't be asking them. These are the deepest questions we can ask. They're worth asking even if we never get complete answers. They're worth pursuing because the pursuit itself is meaningful. Because it makes us more than just biological machines going through the motions of survival and reproduction. The question, what existed before the Big Bang, might not have a simple answer. It might not have an answer at all in the way we typically think about answers. But asking it, pursuing it, exploring the possibilities, working out the mathematics, making observations, testing predictions, that's what makes us human. That's what gives our brief lives meaning and significance in a vast and ancient cosmos. And who knows, maybe someday, maybe in our lifetimes, maybe in our children's lifetimes, maybe centuries from now, we'll figure it out. We'll have a theory of quantum gravity that works, that's been tested and confirmed. We'll make observations that distinguish between eternal inflation and the no-boundary proposal and the cyclic model. We'll understand the origin of the universe the way we now understand the origin of stars or the structure of atoms or the mechanism of biological evolution. Or maybe we won't. Maybe this will be one of those questions that remains forever beyond our reach. A mystery that the universe keeps to itself. A limit to what finite minds can comprehend about infinite reality. But either way, the journey is worth it. The pursuit of understanding, the exploration of ideas, the attempt to grasp the deepest truths about existence that's valuable in itself regardless of whether we reach the destination. It's what makes us more than just animals competing for resources. It's what connects us to something larger than ourselves, something timeless and universal. So the next time you look up at the night sky, think about this. Those stars you're seeing, that light has been traveling for years, decades, centuries, millennia. Some of those stars don't even exist anymore. They've already died, exhausted their nuclear fuel, and exploded a supernova. And we are just now seeing their ancient light. We are looking into the past with every glance at the sky. And if you could see in microwaves, instead of visible light, you'd see the cosmic microwave background, that faint glow from 380,000 years after the Big Bang. You'd be looking back through nearly the entire history of the universe, seeing light that has been traveling for 13.8 billion years. Light that was emitted when the universe was just a baby before the first stars formed. Before the first galaxies caused, and we are asking what came before that, what caused it? What existed before the Big Bang? These are questions that matter. They are questions worth asking. And even if we don't get the final answer in our lifetimes, even if the answer remains forever mysterious, the pursuit of that answer is one of the most meaningful things humans have ever done. Thank you for joining me on this journey into one of the deepest questions we can ask. Thank you for thinking deeply about these ideas, for grappling with concepts that violate our intuitions, for keeping an open mind about the strangeness and wonder of reality. The universe is vast and ancient and full of mysteries. And we are fortunate enough to be here, conscious and curious, trying to understand it all. Keep looking up. Keep wondering. Keep asking questions, because that's how we push the boundaries of knowledge. That's how we honor the gift of consciousness that evolution has given us. That's how we participate in the grand human project of understanding the cosmos, of figuring out where we came from and where we are going and what it all means. The question of what existed before the Big Bang is still open. The mystery remains, and that's exactly how it should be, because a universe without mysteries would be a universe not worth living in. And as long as there are mysteries to explore, there will be physicists and astronomers and curious people everywhere asking questions, pursuing answers, pushing deeper into the unknown. And that's a beautiful thing. That's a profound thing. That's what makes this cosmic journey worth